Here is a good question that summarizes most of what kinetic theory is about. In fact, I encourage you to try it out. Don't just watch the video, but try it out writing some stuff by yourself. So this is ON11 P41. First thing they ask you is assumptions. Now, about 4 or 5 assumptions under the kinetic theory of gases. One of them is already given to you. This is the first one. Gas molecules behave as if they are hard elastic spheres. So when they collide, you don't lose kinetic energy. You just keep colliding with each other and the wall. State 2 other assumptions of kinetic theory of gases. So many, just pick 2. So one of it is that there are no intermolecular forces between the molecules of the gas. Now, you might be wondering, why do I use the word molecules? Why not I say particles? Well, technically, they're kind of the same thing, particles flying around. But if we're talking about gases usually exist as molecules, hence the word molecules, okay? Another assumption, okay, think of another one. Well, you could talk about collision time, or I could talk about volume. Okay, let's talk about volume. So if we're in a container, I'm assuming the volume is negligible lah. The gas particle, it's a round thing, but that volume should be negligible. So I'm going to write that out. Okay, so that is that. So there are 2 marks. All you need to do is, one is intermolecular forces. If you wrote something like that, that's a B1. If you talk about volume, which are of molecules, okay, you must use the word molecules, which are negligible. By itself, it's not going to gain you a mark, but you must say negligible compared to what volume of the container. So this part is very important in order to get your full mark if you want to talk about volume. So other assumptions that you may have talked about is the collision time. Okay, the collision time should be very short when it hits the wall. Another one you can talk about is the rapid random motion of the particles, or I should say molecules. Rapid random motion. So all these are possible answers you can talk about as your assumptions. Very good. Next. Oh, remember this equation? This is the main player of the show, the main equation where we start to do all kinds of fun stuff. We derive this from a box of a particle bouncing around. Remember this? If you can't remember this, go check out the theory video. But using kinetic theory of gases, you can show that this equation is true, where m is the mass of a gas molecule. Now I need to remind you this. People always think m is the mass of the whole gas. No, mass of a gas molecule. So one gas molecule has a mass, and this molecule is flying around. Understand that? Okay, so what is the symbol N? If you can't remember this, it's good to make a list of equations and what every symbol is. So N here is the number of gas particles, or gas, more accurately I should say, number of gas molecules. The masking is sometimes not inconsistent. They accept molecules, sometimes they accept particles, sometimes they only want molecules. So make sure you write molecules lah for gases. What is C squared? This is the favorite one. Sometimes you see people write C squared, sometimes we call it V squared. By the end of the day, it means it's related to speed. Okay, so 3-dimensional speed taken an average. So this C is called mean square speed of gas molecule. Or it just means square speed can already lah. So this one is V1. So yes, make an equation list. And for every term, make sure you know what all these things are, because they can ask you to do things like this. Okay, continue. Ooh, it's a derivation. Okay, use the expression. Which expression ah? Oh, this one up here. Okay. So use the expression to deduce that the mean kinetic energy of a gas molecule is this equation. Now, if you remember how the steps to derive this thing, you should roughly know what to do, but in case you don't know, here's what we need to think about. Okay, we need to somehow get to this. And kinetic energy actually is your good old half mv square, except that this is now c square, because you take the average. So remember that kinetic energy is half mc square. How on earth do we relate that to this? Oh, do you see something familiar? mc square? mc square? So maybe we can do some equating, some magic. So what we can think about is, okay, you know this thing. How do we start? Let us write out some equations. So we know the first one is PV. I'm just going to copy the one from the top. PV equals to 1 over 3 nmc square. This is what we derived. And there's also this thing called the ideal gas law, because we're looking at ideal gas, right? So PV equals to nRT. Or actually in physics, if you see there's a K here, right? KT. There's no RT anywhere. So maybe we'll use the other variation of the ideal gas law, which is PV equals to nKT. K is a Boltzmann constant, so KB or KT. Then you see we can equate things. This is PV, this is PV. So the next step, I'm going to equate. It's good to know how to derive these things, okay? So equate half nmc squared equals to nkbt. Next step, how do we get kinetic energy into the picture? Now if you look at this thing, we have mc squared. We need half mc squared somehow. So we need to do some gymnastics. Maybe I multiply both sides by 3. So this one will become nmc squared. Oh, hang on a second. The n can cancel out. Divide both sides by n. I like. So we have 3 kBT. I'm just going to write K for now. We are almost there. What are we missing? If you look at the pattern up here, we need a half. So we multiply both sides by half. So half. Oh, I think we got it already. So this is kinetic energy. So you can write there average kinetic energy, because you are based on average speed, equals to 3 over 2 kT. Done. So this is one derivation you should know, because they will often ask you to derive this kind of thing. Okay, so 2 marks are. First mark comes from you knowing that, kinetic energy is half mc squared, and also one of the ideal gas equations. And the final one is, if you do some kind of algebra that makes sense and you get to the final answer, then okay already. They'll give you a second mark. Very nice. This question is a good reminder of what we should know. Next, statements. State what is meant by the internal energy of a substance. Now, if you remember, internal energy has 2 parts. You got KE plus PE, and that is what makes up internal energy. But how are we going to state that? So what you can say is, it's the sum, because you are summing up all these things, okay? So first thing is a sum of a random distribution. Why random distribution? Because there are so many particles. Each of them have a slightly different KE, slightly different PE, but we put them all together, you have a random distribution of kinetic and potential energy. So actually there are distribution graphs lah. Okay, it's kind of like become statistic already. But okay, so we have a sum of a random distribution of kinetic and potential energy. Okay, you sum both of those. Of what? Of the substance, of the particle, of the gas. The last part is very important. KE and PE of molecules or particles. So don't simply, it's a KE and PE. Of what? You need to say that. So the first point comes from you talking about a random distribution. Somewhere in your answer, you know that it's a random distribution. So that's A1. If you talk about KE, PE of molecules, particles, that's another mark. Okay, so it's good to practice these kind of questions. Look through what are the points that you need to write. Last one, internal energy. Okay, so they ask you state internal energy. Now they ask you to do something about this. Use the equation to explain, for ideal gas, a change in internal energy is this. Wow, explain this. Why is it this? Just now, what did we derive? Did we derive anything about internal energy? No, we did not. We derived kinetic energy lah. Kinetic energy is 3 over 2 kT. How does that relate to internal energy? So let me show you some very rough working. Internal energy is going to be KE plus PE. But, like we mentioned here, assumptions, there are no intermolecular forces between molecules of ideal gas. Ideal gas only. Okay, so no electric force because of electrons pushing against each other or anything. So that means there should be no potential energy. So this part should be gone. Which leaves me with kinetic energy. And kinetic energy we saw just now is equal to, where is that? 3 over 2 kT. So that means I can say that, oh, U should be equal to 3 over 2 kT. That is the internal energy, which is U proportional to T. Or you could say the change in internal energy is a change in temperature of the gas. And that is what they are asking you to explain. So how are you going to explain this whole step in a sentence? Basically, just describe the whole thing now. So we're going to say, since ideal gas have no potential energy, because we're asking for an ideal gas, we can write that. Hence, no potential energy. I'm going to shortcut and write PE, but I encourage you to write the whole sentence. So that's the first thing. Ideal gas have no more intermolecular forces, hence no potential energy. Therefore, what is left? 3 over 2 kT. So you can say thus. Well, I guess you could write in a sentence. Okay, hold up. Let me write it nicely for you. Thus, internal energy is the kinetic energy of the molecule. Quite neat, huh? And this kinetic energy is proportional to T. Because, U proportional to T. So which is proportional to temperature. Very nice. 2 marks. First thing comes from you knowing that ideal gas should have no intermolecular forces and hence no PE. This is your first mark. Then your second mark talks about internal energy and kinetic energy linked together along with the temperature inside there. So this is your second mark. B1. Okay. Yeah, so this is a very good revision of the kinetic theory. What is it about? What's the main equation? And how do you link that to energy? Okay, of ideal gas, kinetic energy, and things like that. That is all for this example video. I will see you in the next one.